Okay, thanks for the introduction. I'm Jamie, and yes, I will be indeed talking about this wonderful title with a hell of a lot of buzzwords. So the thing I'm going to focus on first is the regular expression aspect. So what are regular expressions? Well, they are a useful tool for doing lightweight parsing tasks. Now, what does that mean? Well, that means they're a very simple set of operations, and they're restricted to parsing so-called regular languages, which are effectively non-recursive. So you get a little bit of iteration, but you don't get general recursion in your grammars. Now, there are a lot of regular expression libraries out in the wild in many different languages, and they usually focus on extracting matched text. So somewhere in some text, there will be some amount of it that matches the expression. Usually they return that text. And, you know, they might look something like this. So I've made a BNF here because it's slightly more convenient to represent them like this. And this is for emails. So you have a user at a domain, which is a bunch of subdomains separated by dots. And that's the regular expression that implements it. And I've used string concatenation here because otherwise there'll be repetition all over the place. So, okay, simple enough. I also want to introduce parser combinators. Now, parser combinators are also a great tool for parsing. They're a bit more general. They can do basically anything. And unlike regular expression matchers, they're concerned with extracting structured results. Now, what that means is, for instance, a programming language AST, or if you have like a small expression language, you might just want to calculate the result of the expression. Parser combinators are concerned with doing that sort of result extraction. So here's an example of parser combinator doing the email example. So here we can see that actually what we want out of it is some email data type. Now I haven't written that here, but it's basically effectively a pair of a string and a list of strings. The first string being the user, the second being the list of subdomains. And the fun thing about them is that you can build combinators that you can reuse for multiple different tasks. So they're all about composing smaller parsers into larger ones. So what's this work all about then? Well, what we set out to do was create a regular expression parsing library that could implement user-directed structured results like a parser combinator library would, and see how fast we could make that. So our main contributions, as listed in the paper, are basically to first show the connection between non-deterministic finite automata and regular expressions via a Cayley transformation. And I'll explain a little about what that is. And then introduce results into these expressions by moving towards more machines instead, and generalizing them to be heterogeneous so that we can support an applicative interface. And finally, to produce an efficient implementation of this via staging. And also discussing the effects of something we're calling staged fusion on the generated code. And this is also something I will get to later. So we've got to start by finding a way to encode regular expressions. Now, the way I've done it here is to implement a data type where each of those constructors corresponds to one of the operations found in regular expressions. So there's ways of reading characters, concatenating two expressions together, trying one expression or another, epsilon, which does absolutely nothing, and a way of repeating an expression 0 or more times, the Cayley star operation. Now, the repetition one is going to be kind of abandoned for this talk because it requires a little bit more special handling and it would not fit on slides. So if you want to know more about repetition, you'll have to read the paper. But here's an example at the bottom, which is how we'd encode a regular expression A, followed by either B or C, and then D. And it's mostly a bunch of literals concatenated together with an alt in the middle to say, well, okay, we either need B or C. So it's as simple as that. And our aim is going to be to hopefully transform this data type and its representation into that of an automaton, right, which represents this same thing. So what about non-deterministic finite automata? Well, these can be expressed in Haskell using what I'm calling widgets. So these are small sort of chunks of an automaton that you can put together to build bigger ones. In this case, we need a way of splitting a state when you leave it, and you can just do that by epsilon transitions. This is why this is a non-deterministic finite automata. It just keeps things simple and reduces the special cases. You also need a state that upon entry requires you to read a character, and then you need the accept state. And if you've consumed all your input and you're left in the accept state, the answer is yes, this matches. So here's an example of that same regular expression implemented as one of these automatons. And it's a little bit hard to see the forest through the trees here. So here is a corresponding diagram. And I've helpfully labeled parts of this diagram by their names in the actual Haskell code. So you can see that we're actually using Haskell's sharing to actually form this join point at the end of the automaton. So how do you connect the dots then? Well, before I can tell you how to connect the dots, I have to introduce a very well-known technique in functional programming called a Cayley representation or a Cayley transformation. And the idea behind this is you have some monoid M. And it might be that the operations on a monoid can be expensive depending on how things have been associated. So you can represent it using the monoid of endo functions, i.e. A to A, specialized to that M. And the idea is whenever you have an M append in your original monoid, you just replace that with function composition. And when you have the M empty, you replace that with the identity function. The most common example of this is the difference list. So this is where you're trying to eliminate expensive plus plus operations that if you associate them the wrong way can build up an n squared complexity by basically just building a function that will concatenate all these lists together. And at the very end, you feed it the empty list, it collapses, and you get a list back in linear time. So a fun thing to note about this is that whenever you apply it, it has the effect of creating a continuation parsing style representation. It's this either a continuation style program or a data structure. This is actually really important for this work, although I won't go into it too much further, because continuation parsing style is really important for the staged aspect and getting nice sort of flow through of the static information. So in the paper, the Cayley transformation appears a lot of times, but it's only going to appear once in this talk. So, okay, let's see if we can get from one to the other. So we start off with regular expressions, and we note that they form a monoid where the M append is concatenation of two expressions, and the unit is the epsilon. So if you concatenate a regular expression with epsilon, you might as well have just not done that. It has no effect, which is what the monoid laws tell us. So, in theory, we should be able to replace them by function composition and the identity function. So let's take a very small example of that, say A's followed by B's, and we're just going to replace that concatenation in the middle, and it's going to be something like lit prime of A composed with lit prime of B. Now, we could ask Haskell to tell us this, or we can figure it out ourselves. The type of lit prime should probably be something like char to reg prime to reg prime. So, okay, we've done that, and you can see it's sort of looking like there's some continuation parsing style going on. Well, we also need a way to finish this, right? When we're building these functions, eventually we'll want a reg prime back. So, for the moment, let's just invent ourselves one of these, and we'll call it final. And that gives us the following type. So we have lit prime with char and a reg prime, or an alt, which doesn't need to change, and final. Now, does this seem familiar? Well, it should seem familiar, because we've already seen it. So we've arrived at the non-deterministic finite automaton representation. Now, the paper goes through this calculation a bit more carefully, but it is effectively the sort of calculation that you might have seen in yesterday's calculating compilers talk. So great, we found a way from regex to the underlying non-deterministic finite automaton. So what now? Well, we should probably finish the compiler for it. So it's very simple, and it's a straightforward CPS traversal. And it just says that we compile a regular expression, and the very last thing to do is accept. And literals transform into items. concatenation becomes composition, epsilon is the identity function, and alternation basically just distributes its continuation across both branches. And of course, repetition's in there somewhere, and I'm not talking about it. So what Next? Well, the whole point of this talk was I wanted user-directed structured results. I haven't got those yet. The problem is that this current automata just doesn't produce these results. It doesn't have anything attached to it. So there's a different kind of automaton called a more machine. And basically, they output a value every time you enter a state. Now, without losing any expressivity or doing any damage, I can say that I'm going to choose to output on certain states and only when they're epsilon transitions. And it doesn't change anything at all, but it does help to keep things a bit more separated. And all that's going to mean is I'm going to add an out state. And you see, magically, I've got an A now. So clearly something's coming out of this. The thing is this only gives us the ability to produce lots of A's during each pass, and that's not sufficient. Indeed, we wanted applicative libraries. We wanted something that can combine different results together and make new results. So instead, what we could do is write these values out to a tape, which is abstractly representing a stack. So it will sort of be a bunch of stack operations that you can later fold up and get values out of. And in this world, pure from applicatives should map to a sort of push operation. You're pushing something onto the stack, and an app reduces those top two elements of the stack to form a new value. So what does this look like? Well, essentially, we have to move to GADT land because we've got to be careful about our type indices now. And the automaton itself is now parameterized by a type level list. And that says what the shape of the stack will be along a given path through the automaton. And most of these don't do much. The two key ones are accept, that says at the very end, when you're accepting something, your stack should contain exactly one thing, and that's the result you are after. So it better be that there's an A on it, nothing else, and you actually did want an A back. The out here tells us how to transform a stack that comes in to a stack that comes out. And those are represented by the op at the top. So if you want to push something, you're saying x's comes in and x cons x's comes out. And if you're doing a reduce, you're saying x cons x to y cons x's comes in and y to x's should come out. So you're basically just showing here that these values are actually going to get manipulated and reduced. So with that all said, how do things stitch back together? Well, it's pretty much the same thing, but perhaps annoyingly, cat and epsilon now do have an effect on the actual automaton. Namely, they've got to do some outputting. So most of it's the same, except here we're going to push a reduce operation whenever we do a concatenation, and an epsilon is actually just going to push a value. So epsilon is now more or less pure, as opposed to being a true epsilon transition as we were originally formulating it. Okay, great. So we now have an applicative interface. We can now do proper parser combinatory stuff. So what now? Well, here's the problem. Here's what's going wrong. Constructing these automatons incurs a runtime cost, and evaluating those automatons incur runtime costs. And maintaining a stack incurs runtime costs. I'm not about runtime costs. I prefer my things to be as fast as possible. So what am I going to do? Well, this is where staged metaprogramming comes in. And if you've never heard of it, it's effectively a technique that gives you very fine-grained control over inlining. And you do that by creating a nice separation between static things and dynamic things. So as an example of this, and I've not chosen the power example, which is the classic staging example. I've gone with something appropriate to parser combinators. This is the exactly combinator, and it does something exactly n times. And we're going to see, what are problems with it? How could it be improved? So the thing to notice about it is, say I know that I want to do something exactly twice. It would be nice if I didn't have to go through the recursion steps every time I did this. that's, a bit redundant. It's a waste of time, and I'm not about wasting time. So I'm going to introduce the idea that the regular expressions are dynamic things. We're going to know them later, but we do know the int now. So I'm going to introduce code around these things, and I'm going to put some corresponding template Haskell quotes and splices in there as well. You don't need to worry too much about them. But effectively, the result is that when I ask the compiler to generate this code, it's going to give me this awful-looking lambda expression. Now, the reason it gave me this awful-looking lambda expression is because I haven't told it anything about the nature of functions. And it turns out functions also have a static structure, right? We know that they have an argument and then they have a body. And if you apply an argument, it collapses. So we can leverage that effectively and squish things more. Now, once we've done that, not only does the code get a bit nicer, but the outputted code is now optimal. So there's nothing more I can do with this. This is as far as I can take the exactly combinator, but hopefully it illustrates this key point. And the key point is less code inside a quote, the better. Because the less things inside a quote, the more things you're doing at compile time. So what about these automata then? What do we do with them? Well, let's imagine we have an exec function. Now, this exec function might look a bit funny. It's got some foldy looking things in it. And the reason I've done that is because these can be parameterized by different semantics. And what are these semantics? Well, you can have stuff like, I want to know what the first match of the regular expression is. Or I want to know, does the regular expression match at all? Or how many times does it match? And by providing these folding functions, you can do this without creating unnecessary lists. So it's quite nice doing it this way, and we'll see that it has some fun consequences when we start staging it. So what do we stage about this? Well, the most available static information here is the automata itself. We should probably know the automata up front, otherwise it would be a bit weird. So I'll pull that out and push everything into code. Now, just by doing this immediately, we've eliminated the overhead of not only evaluating this state, but also building it, right? This is all stuff that now happens at compile time. We don't need to worry about it at runtime. But we can pull the same trick again and notice that this function could be broken up too. And if we do that, we get something that looks like this. So we take in the code of the folding function, the code of the final value, a statically known automata, and this could be composed with the compilation function to get statically known regular expression, and the dynamically known input. Because if we knew the input statically, this would be a very boring exercise. So what about the folding function and value? Can they not be made static? Why have they been left dynamic? Well, the answer is no, at least not for the folding function, because they operate on dynamic values. So we have no way of asking it to do its work on things that we don't know about at compile time. But we could use the same trick we used before and break it up into a code A to code B to code B. Now, what's the effect of doing this? Well, it's actually really cool. And if we look at the definition of first match, any match, and none matches, it's kind of changed a little bit. In particular, these arguments are now meant to be code. So they are not values at runtime, they are values that represent runtime values. And you'll notice that some of them have been ignored. And that's quite interesting, because if we hadn't done this transformation, we'd basically be saying that these would be lazily evaluated things, because it's Haskell, and at runtime, these thunks will be built, but they'll never be touched. So they'll just get thrown away. But that still, takes time to build the thunks, and you could get space leaks out of that. In this case, if you don't touch the code, it doesn't get generated. It's just gone. So by doing this sort of splitting of this folding function, we've actually created dead code analysis that has just ripped these things out. And the underlying generated code is going to be more efficient. And that's what we're calling staged fusion. So this allows us to get different semantics and make that quite efficient when we plug them together. So to give an appetite of, what do these things end up looking like, I have built an example using that same regex that we've seen all the way through, now in its applicative interface form. And once we run that through the entire pipeline, we get effectively a function that pattern matches on strings. Now, there's ways in which this could be improved, but it's a pretty good version for a first attempt. And there's no abstraction in here. Nothing about the regular expression, nothing about automata, nothing like that. It's just raw code. So, okay, well, does it do well? What does it do? Well, here are some benchmarks. This first set of benchmarks is running against some regular expression libraries in Haskell and even one in C. And for this, the semantics picked have been, I think, number of matches, or does it match at all? I can't remember which. But effectively, this one is not producing structured results. And that's okay, because these folding functions have been told to ignore those, so they just disappear from the output. And in this case, these are all relative to our library. So we can see, for instance, it's 60 times faster than text ICU. And in terms of regex TDFA, around 5 to 6 times faster. Now, there are some pathological examples where it gets worse because of the style of backtracking we're doing here, but in general, it seems like it's doing quite well, including against C.
Is that 6 times faster than C?
Yes.
Cool.
Indeed it is. So what about against parser combinator libraries? Well, I only bothered to test out one in this case, and it's a library that I presented at ICFP 2018. And the reason was because this library already outperformed all of the others. So in this case, it seems that at least for 01, this new library is managing to do these regular expression tasks a bit faster. And that might be because of the slightly different backtracking semantics, or because it generates slightly simpler code. Parsley is significantly more heavyweight, although really this is sort of underpinning the underlying principles of how Parsley is supposed to work. However, at 02, GHC seems to like Parsley more. So don't know exactly why that is, but that's how it goes. So in summary then, we've discussed the implementation of a staged regular expression library called Oregano for regular expressions that can produce structured user-directed results. And I've covered a subset of this material here. So I outlined that relationship between regular expressions and finite state automata, and the paper goes into more detail about that. I've outlined how more machines can introduce results and how we can use heterogeneity and parametricity preserving stacks to actually encode applicative operations in these. And I've outlined how staging can be used to improve its performance, including the effect of staged fusion on the generated code comparing different semantics. But more detail on that can be found in the paper. Thanks.